sheet on work power energy. Again, a relatively simple sheet, direct application of concepts that we've learned. Nothing hi-fi about it. Now, so here we have a situation. There is a smooth inclined plane, and there is a mass, almost treated like a point mass, connected to a spring with force constant, spring constant 60 Newton per meter, and with a pulley arrangement of this kind, and this end of the pulley is being pulled with a force 250 newtons. Please, yeah. She has a copy of the sheet. Please sit down. Please share the sheet with her. Yeah. So we have this situation, a smooth inclined plane, a 10 kg mass, and this kind of an arrangement. And the spring comes with an initial elongation of 0.6 meters. Comes with an initial elongation of 0.6 meters. Now, on being pulled with a force 250 Newton, obviously the spring elongates. The spring will elongate. This was already 0.6 meters of elongation. When the mass comes here, the spring elongates by another 1.2 meters. That means 1.8 meters will become the elongation of the spring when the mass reaches this end, because it already has an initial elongation of 0.6 meters. Right? Now, what we are seeking to find is, when the mass reaches this end, right below the pulley, this end, that means this is almost like a point mass. When this mass comes to this position, what would be the velocity acquired by the mass? What would be the velocity acquired by the mass? That is the problem to be addressed. Right? Now, if you imagine the mass along with this as one single unit, along with this string as one single unit, then the forces acting on the mass are what all? There is obviously Mother Earth, mg, acting downwards, right? There is spring force. Since the spring stays in an elongated state, the spring has a temptation to pull it down along the plane, right? And there is an external force 250 newtons. If I include the string as part of the system, then the tension at this point is an internal force, will have no bearing. This would then be looked upon as an external force, not the tension, because I'm looking upon this string as also part of the mass string system. Do you understand what I'm saying? If I looked at the mass in isolation, then I will have the responsibility to not look at this as 250 newtons, but the tension at A acting on the mass would be an external force to deal with. I don't want to do that. I don't want to do that. This is an easier force to deal with. It has a constant direction, constant magnitude, and I would find it an easier force to handle. Okay. Now, anyways, in principle, what are the things that are happening? When the mass goes from here to here, gravity acting downwards, work done by gravity is negative. Right? Work done by gravity is negative. mg minus mg into the elevation acquired. Minus mg into the elevation acquired would be the work done by gravity. Work done by normal reaction is going to be 0, because the displacements are always perpendicular to the normal reaction. So there would be no work done by the normal reaction acting on the mass from the inclined plane. There is spring force which is doing work. The spring has an initial elongation of 0.6 meters. When the mass reaches this point C, the final elongation of the spring would be 0.6 plus another 1.2 meters, which is 1.8 meters. Yes or no? So there is change in elastic potential energy of the spring, and like we learnt in the last class, the work done by the spring force is negative of the change in elastic potential energy of the spring. So all within reach, right? All that we need to do is, and there is work done by this 250 newtons, because the point of application of this would advance to the right by a certain amount. So that would be the work done by this force P. Yes or no? So in principle, in its journey from A to C, this mass, all treated like a point mass located here, in its journey from A to C, we have work done by gravity plus work done by this external force P plus work done by the spring force. That must be from work energy perspective change in kinetic energy. That from work energy perspective would be change in kinetic energy. Yes or no? Right? It starts from rest, and by the time it reaches C, it would have acquired a velocity v. So there is a change in kinetic energy associated with it. Right? Now, one thing at a time. If you think about the additional elevation acquired, this is 30 degrees. So the additional elevation acquired is 1.2 sine 30 degrees. 1.2 sine 30 degrees. Work done by gravity then is going to be minus mg into 1.2 sine 30 degrees. Yes or no? Work done by gravity is negative. Gravity is acting downwards, displacement is upwards. So minus mg into upward elevation produced is going to be the work done by gravity. Yes or no? Now, work done by spring force. Negative of the change in elastic potential energy. Final elastic potential energy is half k xf squared. Initial elastic potential energy half k xi squared. And negative of the change in elastic potential energy is always the work done by the spring force. So work done by the spring force then is minus half k xf squared minus xi squared. Xf is 1.8, xi is the initial elongation it comes with, which is 0.6 meters. Xf is 1.8 meters. You can compute this also, negative of the change in elastic potential energy. That's the work done by the spring force. Now, work done by this 250 Newton force. Work done by this 250 Newton force. Now, just to make the geometry look a little more simpler, the mass was at A initially, and it's on its way to C, which is this point, right? This is the location of the pulley, call it B. This length is given to be 0.9 meters. AC is 1.8 meters, 1.2 meters is AC, right? Yes or no? 1.2 meters. Now, this then is a 3, 4, 5 kind of a triangle. 3, 4 and this will be 5. So this would be 1.5 meters. Do you realize that? AB. This length AB then would be 1.5 meters. Do you all realize this? Right? It's a 3, 4 and therefore 5. 3, 4, 5 kind of a triangle. Right? Good. Now, when the mass migrates from A to C, when it was at A, the part of the string to the left of the pulley is 1.5 meters. And then once it arrives at C, the part of the string to the left of the pulley would be 0.9 meters. This would become the string. That means to the left of the pulley, how much of string length has been freed? 0.6 meters. Yes or no? 0.6 meters of the string length has been freed. And where will it appear? That 0.6 meters will appear here. Yes or no? Therefore, the point of application of this force P would advance by 0.6 meters. Yes or no? Therefore, the work done by P then, would be 250 into 0.6. These many joules would be the work done by. Yes, I'll explain again. No issues. See, this is 1.5 meters. This is 0.3 meters, right? So this is roughly almost like a point pulley, right? So this string length is 1.5 meters. This string length is 0.9 meters. That means string length to the left of the pulley on this side of the pulley has decreased by 0.6 meters. Isn't it? Where will it appear? It will appear in the advancement of the point of application of this force P. That means the point of application of P would advance by 0.6 meters. Work done by 250 Newton force is going to be 250 into 0.6, 150 joules. That's going to be the work done by P. Yes or no? Got me right? Right? So now we have everything in place. We know all of this. And then we are ready to compute the change in kinetic energy. It starts from rest, zero kinetic energy. By the time it reaches this point, it would have acquired a velocity v. So the change in kinetic energy is half m v squared minus 0. And this would enable computation of v. So this is work energy perspective. This is work energy perspective. How about it? Right? Now, there is a mass m which is connected to a spring whose original natural length, unstretched length is L0, right? Essentially, originally the mass was here in this state where the spring was unstretched. The spring was unstretched. And there was a force F there was a force P, let's say, that was tangentially pulling the mass M. That was tangentially pulling the mass M, making sure that the mass M essentially did not develop any velocity. This is like what is in physics parlance, it's commonly referred to as a quasi-static force. It's being pulled very, very slowly, quasi-statically. That means from point to point, it remains in equilibrium. The force P just about manages to move the mass along the circumference of the sphere tangentially. This is frictionless. It just overcomes the forces acting on the mass M and just about pulls the mass M to nearer and nearer positions. Theta was originally 0, the mass was here, and finally the force P that was tangentially acting on the mass, this was a variable force. This was not a constant force, this was a variable force, because a constant force couldn't have maintained the mass in equilibrium for all positions of the spring. That was not possible. So this was a variable force in any case, maintaining the mass in equilibrium from position to position, and eventually the mass was brought to this position from rest to rest. From rest to rest, there was some amount of work done by this force P. We want to be able to compute the work done by this force P. Obviously, you know, the mass eventually went from rest to rest. That means all forces acting together would have produced no network, because the net change in kinetic energy is 0. The mass was originally at rest and it finally was at rest. So what was the change in kinetic energy? 0. So what was the work done by all forces put together? 0. Okay. Now, in this state, what is the elongation in the spring? 0. Right? So elastic potential energy of the spring, U1, is 0. That's the elastic potential energy of the spring in this state. Because I'm seeking to compute the work done by the spring force first. Work done by the spring force would be negative of the change in elastic potential energy. Now, when the spring comes to this state, realize that this is the extent of elongation produced in the spring. This circumference length is the elongation produced in the spring. If this is theta naught, then this length is a theta naught. If theta naught is in radians, this length is a theta naught. That's the elongation produced in the spring, yes or no? S is r theta, right? So what's the elastic potential energy of the spring in state 2? Half k a theta naught squared, yes or no? So what's the work done by the spring force? The work done by the spring force is going to be negative of u2 minus u1. Negative of u2 minus u1, u1 is 0. Right? That's, so we already know the work done by the spring force. Yes or no? Now, when it comes to gravity, gravity has been acting all along vertically. And this is from state 1 to state 2. This is the elevation produced. If A is the radius, then this is A sine theta naught. This is A sine theta naught. That's the elevation produced. Yes or no? So, what's the work done by Mother Earth? Minus mg into A sine theta naught. Yes or no? This is A sine theta naught. That's the work done by Mother Earth. That's the work done by gravity. Right? All's good? Yes. Now, all along, there has been a normal reaction from the surface. But the normal reaction is always perpendicular to the tangential direction. So work done by n is 0. Work done by n is going to be 0. We are now all set, because work done by P, which is what we want to compute, work done by the spring force, which we have already obtained, plus work done by gravity, all of this must be change in kinetic energy, and therefore 0. This then gives us an opportunity to obtain work done by P. Work done by P. Yes or no? Clear? Where there is a long plank resting on a smooth surface. Initially the plank is at rest, and this mass m is given a velocity v0 to the right, and the interface between small m and capital M is rough, and the coefficient of friction between small m and capital M is given to be mu, right? Now what we want to be able to compute is work done by friction on small m by the time small m comes to rest with respect to capital M. Now what does it mean by saying small m comes to rest with respect to capital M? That means they acquire the same velocity. Why on earth would they acquire the same velocity? Realize that there is friction acting on it, kinetic friction, approximately maximum static friction, mu mg leftwards, which will retard this small m, right? And as a reaction to this, small m will exert on capital M mu mg to the right. This will accelerate capital M. The velocity of this will deplete, the velocity of this will grow, right? Eventually the velocity of capital M, so velocity of small m will deplete, velocity of capital M will grow. Eventually they will acquire a final common velocity, and then once they acquire a final common velocity, which was the handiwork of friction, there would be no further relative motion beyond that point. There would be no further relative motion beyond that point. I want to be able to compute the work done by friction on small m by the time small m and capital M acquire a final common velocity v. You know what I'm saying? Now, realize that this is capital M, this is small m, and the two as one single unit eventually acquire a final common velocity v, right? Now if I look upon small m and capital M as one single unit, if I look upon small m and capital M as one single unit, then what are the external forces acting on the system in the horizontal direction? So let's say in general, all the external forces acting on the system comprising small m plus capital M is small mg and capital Mg. Those are external forces courtesy Mother Earth, right? Then there is normal reaction from the ground, which is also an external force in a system comprising small m plus capital M. But whatever small m and capital M are doing to each other in terms of the normal reaction prevalent between them is internal. Even this frictional force is internal. In the horizontal sense, therefore, on a system comprising small m plus capital M, the net of all external forces is 0. On a system comprising small m plus capital M, net of all external forces is 0. Yes or no? Now I can explain it again if you're lost. Explain again. I'm saying, look at a system. See, if I look at small m alone, this is an unbalanced force in the horizontal direction. If I look at capital M alone, this is an unbalanced force in the horizontal direction. But if I look at small m plus capital M, then these two forces are internal forces and they would cancel off in pairs, right? Their status is reduced to 0. On a system comprising small m plus capital M, the net external force in the horizontal sense must be 0. Only for a system comprising small m plus capital M, right? And therefore, in the for a system small m plus capital M, the horizontal linear momentum must be preserved. The total linear momentum that the system started with was mv naught. Yes or no? That is what it started with. And eventually when it arrives at this state where small m and capital M acquire a final common velocity v for reasons I mentioned, the total linear momentum of the system is small m plus capital M into v. In absence of any net external force in the horizontal direction, for the system constituted by small m plus capital M, the linear momentum must be preserved. No external force acting horizontally. Therefore, linear momentum must be preserved for the system. Yes or no? You know what I'm saying? And therefore, the final common velocity is like mv naught by capital M plus small m. What's the change in kinetic energy of small m? Change in kinetic energy of small m is half small m into v squared minus v naught squared. Very clearly, v is less than v naught. V is less than v naught. Can you see that? Because small m by capital M plus small m is less than 1. So v is evidently less than v naught. And if v is less than v naught, very clearly this is negative. And who brought about this change in kinetic energy of small m? It was friction. Work done by friction was instrumental in bringing about this change of kinetic energy of small m. So this then, would you not want to believe, is the work done by friction on small m? This then is the work done by friction on small m. Change in kinetic energy on small m. Who brought that? Friction. And it's a negative number. Why? Because frictional force is acting leftwards and displacement is rightwards. So work done by friction ought to have been negative in depleting the velocity of small m. What do you say? We have computed from linear momentum conservation of small m plus, but linear momentum couldn't have been conserved for small m, couldn't have been conserved for capital M alone, but could have been conserved for small m plus capital M, because together this force and that force would cancel off. They would be looked upon as an internal force cancelling in pairs. Right? One problem. There is a spring with force constant K, and this position is referred to as the natural length of the spring. Right? This mass M is slowly moved to the right, elongating the spring by an initial amount 3 mu mg by K. Alright, and there is coefficient of friction between small m and the ground given to be mu. Right? Now, let us see how this system will behave if released from the state. Once small m is released from the state, let's see how it's going to behave. Okay. The spring force in this position of mass m is going to be K times xi, initial spring force. K times xi, which is 3 mu mg, yes or no? K times xi is 3 mu mg acting leftwards, isn't it? Spring force, initial spring force. And which is good enough to overcome mu mg, the coefficient of the frictional force, maximum static friction between small m and the ground. And this will therefore propel small m to move leftwards, move in this direction, because Fi is good enough to overcome mu mg. Obviously, spring force would have acquired its maximum value mu mg. Frictional force would have acquired its maximum value mu mg in this state. Yes or no? Right? Now, so this is time t equal to 0. This is time t equal to 0. Spring force Fi to the right and kinetic friction, maximum static in this direction. Right? So what is the acceleration initially? Net force, which is 3 mu mg minus mu mg, right, by m, which is 2 mu g. 2 mu g is the initial acceleration leftwards. Spring force Fi minus mu mg divided by m. That's the acceleration in this direction. Initial acceleration of small m, right? It starts from rest. Now the mass is obviously going to develop velocity leftwards because spring force initially and for a while will be larger than maximum static friction. It would develop velocity in that direction. Spring will then keep coming closer and closer to its natural length. Spring force will keep decreasing. Spring force will keep decreasing. When the mass passes this position, natural length of the spring, spring force would have become 0. Right? And there is only friction to the right. But then by this time, the mass would have developed a velocity leftwards. And therefore, because of that velocity, it will compress the spring. It will compress the spring. Now, the spring will be vehement towards this compression. It will push the mass rightward. It will exert a rightward force on the mass. And friction will also act rightwards. The mass will retard. The mass will retard. And eventually, the mass would be brought to rest after having got compressed, let's say by an amount xf. After having got compressed by an amount xf, the mass would be brought to rest once again. Yes or no? Now once that happens, this was the initial state of the mass. This is the final state of the mass. Between these two states, I'm going to deploy work energy theorem. I'm going to deploy work energy theorem. I seek to compute xf. I need to compute xf, the maximum compression. Compression over and above its natural length. Okay? First things first. What is the work done by the spring force between this state and this state? Work done by the spring force is always negative of the change in elastic potential energy, which means minus half k xf squared minus xi squared. Xi we already know, 3 mu mg by k. That's the work done by the spring force, negative of the change in elastic potential energy. But at this state, the elastic potential energy is half k xi squared. In this state, half k xf squared. Yes or no? Right? Work done by friction. Friction is acting in that direction, displacement is occurring in this direction, right? So what's the work done by friction? Minus mu mg, which is in that direction, and displacement in this direction. Xi plus xf? Xi plus xf? Is that not the work done by frictional force? Normal reaction and gravity are perpendicular to the displacements, doing no work. Right? And therefore, sum of these two must be change in kinetic energy, which is 0. Because from rest to rest. Why is this a rest position? Because this is a state of maximum compression. If it had residual velocity, even in this state, it would compress further. Not the case, right? So, work done by spring force plus work done by frictional force up to the point of maximum compression would be change in kinetic energy, which is 0. Right? So, we have like a minus half k xf squared minus xi squared minus mu mg into xi plus xf. That must be 0. I can divide throughout by xi plus xf. That will simplify the algebra a little bit. Minus half k xf minus xi xf minus xi minus mu mg. That must be 0. And very clearly this plus this must be 0. And kxi is 3 mu mg. So half kxf and half minus half kxi. Kxi is 3 mu mg plus mu mg is 0. I hope you realize whatever I did here. I've replaced this kxi by 3 mu mg. Right? So this would be minus half mu mg going on that side. So kxf is mu mg. xf, the maximum compression, is mu mg by k. That's the maximum compression, yes or no? From this point onwards, you didn't understand. This point. You didn't understand how I got this. Okay. Look at this equation. I divide by xi plus xf. So I get xf minus xi. Right? Then this kxi I replace by 3 mu mg. So minus 3 mu mg by 2 plus mu mg is kxf. Half will get cancelled. So kxf is this. What? Still confused? So xf is mu mg by k. Now, there is another part, I guess, to the problem. Let's see what that is. Maximum compression. So we already know this. The maximum speed of the block. Let's compute the maximum speed of the block during the journey. But all's good so far, right? Let's physically first understand the position where you would expect the speed to have become maximum, right? Let's physically analyze this. Can I remove the clutter from here? You really think at the natural length? Let's see. Let's see. So some of you believe that at the natural length, the speed will be maximum. Let's understand this, don't worry. Let's figure out. Let's figure out the physics involved in computing the maximum velocity during this journey. Maximum velocity during this rest to rest. At what point and why? Can I just remove all this? See what happens. Look, when the mass started from here, spring force Fi, kxi 3 mu mg is greater than mu mg. It had a leftward acceleration. As the spring kept losing its elongation, the spring force kept decreasing. But as long as the spring force was more than mu mg, spring force started with 3 mu mg by k, 3 mu mg, and it decreased because this xi decreased, right? But as long as the spring force remained greater than mu mg, there would be an acceleration in this direction. Even though the acceleration will decrease, the velocity will still increase. Acceleration decreases in this direction, but velocity will still increase, right? At some point, at some instant, some point of the spring, the spring force would have become mu mg. The spring force would have become mu mg. See, it started with 3 mu mg. At some point, it will become mu mg, whereby it's just about going to balance the frictional force mu mg. Until this point, the spring force was more than mu mg. The particle accelerated, though at a decreasing rate. Now, there would be then an instant when the spring force will become mu mg. Yes or no? The spring force will become mu mg. When the spring force becomes mu mg, it just about balances frictional force. Acceleration becomes 0. Yes or no? Now, the velocity would have acquired a certain velocity, say Vp. The velocity would have become Vp by this time. It had continuously accelerated. From 0, the velocity continuously increased and it became Vp, though with decreasing accelerations. Now, from this point onwards, the spring force will further decrease. Right? Spring force, when the particle overshoots this mark, will become less than mu mg, less than frictional force. That means now frictional force will be more than spring force. Now it will retard. So velocity will decrease. That means this must be the point of maximum velocity. This then must be the point of maximum velocity. Yes or no? Because from this point onwards, spring force will be less than mu mg, frictional force will be more mu mg, and therefore it will retard. Right? So at a point where the acceleration becomes 0, the velocity would have acquired a maximum. Yes or no? So which means now I want to be able to compute Vp. I want to be able to compute Vp. First of all, how much must have been the elongation in the spring? X naught. The elongation in the spring at P. Elongation in the spring at P must be x naught, where kx naught just about becomes equal to mu mg. Yes or no? So elongation in the spring at P is mu mg by k. Is the elongation in the spring at, right? Now, between this initial state, this state, I will apply work energy theorem. I'm going to apply work energy theorem, where I know xi, the elongation in the spring here, I know x naught, the elongation in the spring here. What's the work done by the spring force? Minus half k x naught squared minus xi squared. Where x naught, we've computed, xi we knew, right? That's the work done by the spring force, negative of the change in elastic potential energy. Then what's the work done by friction? Minus mu mg into this length, which is xi minus x naught. This length is, realize this whole thing is xi, this is x naught. So displacement of the particle is xi minus x naught. So xi minus x naught. Right? Now, this then must be change in kinetic energy, half m Vp squared. This then must be change in kinetic energy, half m Vp squared. Xi we know, x naught we know, and we are eligible for this computation. Right? We can compute the maximum velocity Vp during this entire journey. It happens at a point where the acceleration becomes 0, because overshooting this mark means frictional force would supersede spring force, the particle will retard. Right? Situation where this mass is at rest initially and this theta is 30 degrees. Eventually the mass descends and this theta becomes 60 degrees, 3m comes closer, right? So what happens eventually is, when this mass would have reached the ground, this mass m would have reached the ground, say it would have acquired a velocity v1, and this mass 3m would have acquired a velocity v2 like this, and this angle would have become 60 degrees. This is what would have eventually transpired, right? So then, from this state, theta equal to 30 to theta equal to 60 degrees, let me apply energy compliance. Work done by gravity, mgh. Where does it appear? Half mv1 squared plus half of 3m into v2 squared. Yes or no? Now there is going to be a string constraint that is going to connect v2 and v1. and which we can plug into this and obtain both V2 and V1. That's the whole idea. This is energy, and next one is a geometrical constraint of the problem. Now, V2 resolved along this direction, V2 cos 60 degrees, V2 by 2, isn't it? V2 cos 60 degrees. All velocities to be taken along the length of the string. This is 0. This is 0. This would be V1 downwards, integral with this mass m, right? I hope you haven't forgotten all of this. V1 like this. This would be 0. Then I go from this end to that end. This is one single string, right? So I have like a 0 minus V2 by 2 plus, this is the wraparound length constant. Then I say like a V1 minus 0, right? And then I go this way, 0 minus V1, 0 minus V1, 0 plus V1, all of this must add up to 0. So this gives me a connectivity between V2 and V1, yes or no? So this gives me like a V2 equal to 4V1, V2 equal to 4V1. You can plug in V2 equal to 4V1 and obtain the value of V1 and therefore also the value of V2. So, two very ordinary things with which you were familiar, you had to apply in a very simplistic manner. Any given topic would eventually have only 5 concepts. C1, C2, C3, C4, C5, 5 concepts. Any problem in that topic would either involve C1 or not involve C1. 2 ways of dealing with C1. 2 ways of dealing with C2. 2 ways of dealing with C3. 2 to the power 5. Now, but this includes that one case which involves neither C1 nor C2 nor C3 nor C4 nor 32. No, but that one case is included here. Because the best problems in a given topic don't even involve one single concept from that topic. When I do permutation combination with you, you'll realize the best of problems would be free from everything that I have taught to you. Those are the most fundamental problems. Yes. So 32 variations in all, yeah? In all 32 variations. That's it. It's an easy thing to deal with, isn't it? Problem, please, all of you, your attention, please. So, this block M resting on the ground, okay, and the two connected by an ideal spring, and the spring is compressed, right? And the two masses are held together by a thread, right? They are at rest. The spring is compressed and they are held together by a thread, so that the masses don't, right, move. And once the thread is burnt, the mass M would be pushed up because of spring force. Question is, eventually, how much should I compress the spring initially, x naught? How much should I compress the spring initially, x naught, so that once released from the state, this small m at some point will lose contact with the ground? You know what the problem is? Have you all understood the problem? Now, this was the line of natural state of the spring. This was the line of natural state of the spring. It was compressed by an amount x naught. Now, first of all, let's understand the vulnerability of this mass to lose contact with the ground. When and how and why? When would it lose contact with the ground? Okay. So, from this state to this state, so when the mass is being pushed up by the compressed spring, the mass would acquire velocity. The mass would come to this point. But between this state and this state, the spring remains compressed. And if the spring remains compressed, it's going to keep pushing the mass m downwards only. And therefore, while the mass traverses from this point to this point, there is no prospect of the lower mass losing contact with the ground, because spring remains in a compressed state during this journey, and the spring force will push the mass m downwards. There is no prospect of this mass m losing contact with the ground. Right? Now, once the mass comes to this point, once the mass m comes to this point, because of spring force, it would have acquired a velocity v, right? It'll overshoot this mark, therefore. It'll overshoot this mark. And once it overshoots this mark, the spring will now begin to blow up in the elongated state. The spring, right? Beyond this point, the spring will get elongated, isn't it? This is the elongation regime. This is the elongation regime. This is the compression regime. Clear? Now, once the spring gets elongated, the spring will exert an upward force on M, and this mass M, if the spring force will just about become equal to mg, then small m is on the verge of losing contact with the ground. If the spring force, see, beyond this point, at some elongation of the spring x1, when the mass comes to this point, the spring gets elongated by an amount x1. Right? Now the spring would want to get back to the state. So the spring force now would be kx1 upwards. Right? And the kx1 that would cause m to lose contact with the ground would be given by kx1 equal to mg. Kx1 equal to mg. That x1 will cause this small m to lose contact with the ground. Yes or no? Right? So you want eventually this mass m to start from here, reach the natural state, and certainly acquire an elongation at least to the tune of x1, so that small m loses contact with the ground. You want this to happen. That means, even though from this point onwards the mass small m will retard. Why? Because the spring is going to pull it down. But you at least want the mass to come to this point, even though with zero velocity, you at least want this mass to reach this elongation state x1, even if it means it reaches this point with zero velocity. Then also the spring force will be kx1 to pull the mass m off the ground. Yes or no? Right? x1 is the extent of elongation that you eventually want. Such should be x0. That means it starts from rest and at least goes to rest. Right? At x1 it at least goes to rest. Between this state and this state, let me apply work energy theorem. Right? I know x1 is mg by k. I want to be able to compute x0, that will cause x1. Right? Now, what is the work done by gravity between these two states? Minus mg into x0 plus x1 is the work done by gravity. Would you believe this? Displacement is upwards, mg is downwards. This is the work done by gravity. Right? Work done by the spring force. Negative of the change in elastic potential energy. What's the elastic potential energy here? Half k x1 squared. What's the elastic potential energy here? Half k x0 squared. So negative of the change in elastic potential energy, x1 squared minus x0 squared. That must be change in kinetic energy. That's 0 to 0, rest to rest. Yes or no? Yes. If I suppress it by an amount of x0, it will at least reach x1 with zero velocity, if x0 is obtained from now. This is no issues at all, because again I can divide by x1 plus x0. So first of all this, and this will give me mg plus half k x1 minus x0 equal to 0, dividing by x1 plus x0. Right? Now kx1 is mg very clearly. Kx1 is mg. So this kx1 that comes here, I can replace that by mg. So mg by 2 plus mg, 3mg by 2. Yes or no? So kx0 by 2, this kx0 by 2 is 3mg by 2. Yes or no? So this gives me x0 equal to 3mg by k. This work done by gravity. Okay, I'm saying, okay, from rest to rest. I'll give you one more funda. Suppose it obviously starts from rest, and I want it to reach an elongation state at least x1. Right? So suppose it comes to rest. What should be x0? Suppose at x1 this mass comes to rest, what should be x0? That's what I have computed. How much should x0 be so that if an elongation x1 is reached with 0 velocity, right? So that x0 is this. Now. If I compress it by an amount more than x0, if I compress it by an amount more than this x0 that I have computed, then also it will reach this point but with a non-zero velocity, That means this is the smallest amount by which I must compress so that it at least reaches this point which will cause, right. So if I compress it by an amount more than x0, it will still reach x1 but with now a non-zero velocity. That is the whole idea. Got me?